Hello and welcome back to another lecture on the NPTEL course on advanced plasticity of solid continua. So, in this lecture we will be giving you a scientific rationale behind the use of the rate functional whose variation set to 0 gives us the governing equations, right, including the flow rule. And also we will be discussing, if time permits or otherwise shortly afterwards, that is in the next lecture, we will be discussing time discretized variational updates, right, so which can be implemented in a computer. So these are all in the context of thermoviscoplasticity of the Parzina type that we have been discussing. All right, so let us get started. Now let us talk about the rate functional, right. So if you recall that the rate functional is the derivative, time derivative of psi, the free energy, plus the dissipation potential, right, integrated possibly over the domain. Now, and we have been formulating all our constitutive evolution laws derived from these rate functional, right. That is from the dissipation potential, which is a part of the rate functional, or their duals. Now, within the limited mathematical setup that is permitted within this course, I will try to answer the following question, right. Is there a principled scientific justification for characterizing the evolution of plastically deforming solids as the minimization of this rate functional? Okay. If you recall that in elasticity we do not have any rate functional, we have a functional in the form of the strain energy. It is not anything related to the time derivative, or it does not give a rate. This is slightly different, but in principle, provided you get yourself, you accept that difference, otherwise we have the same variational principles applicable to both elasticity and the plastic solutions, right. So we have seen that this rate functional gives us laws which are thermodynamically consistent, right. It satisfies the second law and all that. But we want to know if the minimization of this quantity is really what gives us the solution, right. Why is it? So let me try and provide a systematic justification, even though a very precise justification is not within the scope of this work, of this NPTEL course. We will try to combine very briefly some aspects of non-equilibrium thermodynamics, because as you know, plastic flow is not equilibrium thermodynamics, right, it is non-equilibrium thermodynamics. We will use certain aspects of convex analysis and certain additional insights from certain stochastic principles that you need not know, but I will just tell you very briefly, just so that your mind is set at rest as to the use of this rate functional as a valid objective to minimize, to get your solutions. Now let us begin with the first and second laws, right. So for a thermomechanical systems, as you know very well, that the dissipation inequality will have this general form given here, right. The left hand side, this calligraphic D gives you the dissipation, that is the power dissipated that is per unit time, the energy dissipated per unit time. Now recall that eta is basically the entropy which is related to the minus del psi by del theta. Psi is the free energy, right. X is basically the thermodynamic conjugate to alpha dot, where alpha are the internal variables whose evolution describe plasticity, if you recall. Okay, so X is minus del psi by del alpha, and Also sigma is equal to del psi by del epsilon E, where epsilon E denotes the elastic part of the strain. All right. So these are the things we have already seen. These are the thermodynamic relations, all derivable from the Coleman-Knoll procedure. Now we can actually use this to the kinematic decomposition, if we can do, the kinematic decomposition means epsilon is split into epsilon E and epsilon P. If there is an epsilon thermal, that is strain due to the thermal expansion or things like that, then that also can be included. Then epsilon P dot is the plastic strain rate, then you have the following expression for the dissipation, where G is basically the minus grad theta by theta. Theta is the absolute temperature, Q is the heat flux. Okay. So this is the dissipation, which has to be greater than or equal to 0. Now if we introduce the generalized forces, it can be written in a very simple manner. For example, this is a force like quantity, right, sigma. It acts on a kinematic rate like object. Similarly, this is a force like quantity. It acts on a rate like object. Think of this Q, heat flux, also to be a force like object. Okay. And then if you club all these things together in a single variable called sigma, okay, and club all the kinematic rate like variables. Of course, G is not really a rate like variable, but nevertheless you just club G with the rest of the rates and write it as Z dot equals epsilon P dot, alpha dot and G, club them together. Then the dissipation inequality has a very simple form. It is just the generalized force with a proper inner product with the generalized rate, correct, that is greater than or equal to 0, right. So this inequality is the only thermodynamic constraint imposed on the constitutive equations, right. This is the only constraint. Now in order to ensure that this inequality is valid for all admissible processes, we have also introduced the convex dissipation potential phi, right. Phi is a function of the rates z dot and theta, okay. And we have postulated the general constitutive relations, because if you take the subdifferential or the gradient, if it is sufficiently differentiable, of phi with respect to these rates like z dot, then what you get? You get the corresponding thermodynamic conjugate. In this particular case, the generalized thermodynamic forces sigma. You should recall that. Okay. And similarly, from convex duality, this is, we have called this as the flow rule, right. This is what we have called the flow rule, or basically the constitutive relations. Or equivalently, it can also be written in terms of the dual. That means instead of writing sigma on the left hand side, if we write z dot on the left hand side, that can be found from the partial derivative of phi star with respect to sigma, or if it is not adequately differentiable, from the subdifferential of phi star, okay, with respect to sigma. Recall that phi star is the dual convex dual potential, dissipation potential, and it is the Legendre-Fenchel transform of phi. All right. Now with this arrangement, recall the Fenchel-Young inequality that we covered towards the beginning of this course, probably in the 7th or 6th lecture or somewhere. So you can go back to that particular lecture if you have forgotten about it and refresh your memory before coming back to this particular slide. Okay, so it's a good idea. So the Fenchel-Young inequality generally gives you that the sum of phi, which is a function of the rate like variable z dot, and phi star, which is a function of the thermodynamic generalized thermodynamic force sigma, must be greater than or equal to the total dissipative work done, which is basically sigma inner product with z dot. All right. Now recall that the equality I mean this becomes an equality strictly only when sigma is found from the subdifferential, that is from the gradient of phi, or equivalently if z dot can be found from the gradient of phi star with respect to sigma. Okay? So, when you do that, that means when you get the actual flow rule, that is when you ensure that sigma is such that for which the material evolves according to that particular sigma, then this becomes an actual equality, right. So along all these admissible evolutions, therefore, what we have is that the sum of phi and phi star is equal to the inner product of sigma and z dot. That is a very important thing, right. Now, let us also understand another thing, right. So, if you take the total time derivative of psi, right, then you get something like this: psi dot is sigma epsilon dot minus sigma inner product z dot, right. Now, understand that this sigma inner product epsilon dot is the total, power that is available for this solid body to expend against various heads, right. Suppose you have a lot of some money, so you want to apportion the money for certain purposes, right. So, sigma epsilon dot is the total plastic power, not plastic power, the total power that is available for the body given the external loading, right. So, part of that goes into the plastic work, part of that goes into the hardening mechanisms, part of that is dissipated and things like that through heat and all that, right. So, substituting this psi dot, this expression, into the duality identity, right, then you see that the sigma z dot can be written as sigma epsilon dot minus psi dot, right. So, we can write this as that same Fenchel equality can be written in this manner, right. So, this just rearrange, So, what do we have? Just rearrange means, by that I mean just keep this psi dot plus phi of z dot on the left hand side, which is the rate functional that we have been taking variations of, and the rest of the items on the right. So, on the right what is there is the total power that is available, that is fixed, you can't do much with it, and we also have minus phi star sigma, right. So, remember that when we actually take the variation, we do not take the variation of sigma, that is the force like quantities, and the thermodynamic, the conjugates, the rate like quantities together, right. That is wrong, because when you take the variation of z dot, automatically sigma has to adjust itself with that z dot. So, you cannot take the variation of both together, right. So, we take typically the variation of z dot, right. Then in that case we keep sigma fixed. If sigma is kept fixed, that would mean that while taking the variation, phi star sigma will be untouched, will remain the same, right. So, this is fixed, this is also fixed. So, what we try to do is basically, we try to, but sigma still is a function of z dot, right. So, we try to minimize this part, okay. Equivalently, if we try to vary sigma, then we try to maximize this phi star, that is minimize minus phi star sigma subject to thermodynamic consistency, that means subject to the relations that actually relate sigma with z dot, right. So, the minimization of psi dot plus phi z dot is equivalent in a way to the maximization subject to constraints of phi star as a function of sigma. Now, that is what exactly we have said here. For a prescribed loading condition, the external power sigma epsilon dot is fixed. So, the evolution essentially is governed by the minimization of psi dot plus phi z dot, right. And also this is equivalent to maximizing phi star, right, subject to the thermodynamic constraints. So, the minimization requirement is that the stationarity condition has to be satisfied. That means 0 must be in this set, that in other words 0 is equal to this if things are sufficiently smooth, right. So 0 equals the derivative of psi with respect to z and the derivative of phi with respect to z dot, right. So which is nothing but, so you see that basically what is happening here is that this relationship, because del phi dot is basically nothing but sigma, right. So basically this just says that and del psi by del z is also related to sigma, right, because you have from psi dot equals del psi by del z, right, z dot. Now this you call as minus sigma, correct. So basically what you do is that in both the cases, I mean so sigma is related not just with phi but also with psi, right. So so this relationship is nothing but this relationship, that is sigma is found from the gradient of phi, right. So thus the constitutive equations arise, but this is basically the Euler-Lagrange equation of my psi dot plus phi, right, my rate potential. So the constitutive equations arise as the Euler-Lagrange equation of the rate potential, you understand. You know that, right. If you take the variation of an objective functional, you get the Euler-Lagrange equation, which are the governing equations for the solution. For typically in mechanics we get the governing equations in the form of, let us say, the linear momentum balance or the constitutive relations, okay. Now this interpretation has to take a slightly advanced level, because we have still not perfectly argued out that why is psi dot plus phi has to be a minimum. Okay, so at least one thing is very clear, that psi dot is the rate of change of the stored energy. So it is the change of energy, stored energy. Phi is the rate of dissipation. So the total thing is the total rate, their sum represents the total energetic cost which must be expended for the evolution, right, excluding of course the externally prescribed power, because externally prescribed power is given only by the external loading, right. You do not have much control over that in analyzing that. Once the loading is defined, we do the rest of the analysis, right. So what we are trying to do when we are trying to minimize this, we are essentially minimizing some incremental energy, okay, which is needed for the evolution of the in this particular case plastic flow, right. Now this comes the deeper aspect of it, which is the statistical mechanical interpretation, right. This is the proper justification of why psi dot plus phi has to be only a minimum, not a maximum, right. In fact, this is basically using some basic aspects of statistical mechanics, right. At the microscopic level, the plastic deformation arises through many microstructural events which are essentially random in nature. For example, you think of dislocation motion, it is highly random. It happens in an intermittent manner. Sometimes if you see through a microscope, an electron microscope, you will see the dislocations to be stationary for most of the time, and then they suddenly jump, right. So it will be looking pretty random. The molecular rearrangements which are needed sometimes for the crystal reorientations and things like that, they are also quite random in nature. So a coarse-grained description which would lead to a proper equation at the macroscopic level for the solution, if you account for all this randomness together, so the coarse-grained description must lead to a stochastic evolution for the internal variable z, correct, because all this randomness that are there in the microstructure will not be resolvable at the macroscopic level, so therefore they will appear as noise. So whenever they will appear as a time dependent noise, it has to be treated as a stochastic process, okay. So basically these are noisy trajectories z. So such stochastic systems can be modeled by what are called the diffusion processes, right. So the diffusive stochastic processes like Brownian motion or functions of Brownian motion. You know, Brownian motion is a typical diffusion process. You know, the way that if you put a drop of ink into a bowl of water, the way that the ink disperses, the way that that drop of ink spreads throughout the volume of the water as time progresses, that is a typical case of the Brownian motion, right, diffusion process. Right, so such stochastic systems are typically diffusive, or if they are not modeled as a diffusive stochastic process, they may be modeled also by what are called the jump processes, right, because essentially the dislocation motion happens through jumps, right. So you can model them through jump processes also. But be that as it may, in both the cases, you know, if you think of z to be a stochastic process, it is a path process. That means a knowledge of z at a given time is not that important as the knowledge of z over a path, right, varying when the time varies from 0 to capital T, let us say, okay. So the probability of that path of z, which is the variable of interest, to describe plastic flow at the macroscopic level is related to, except for some factors which are constants, that probability is nothing but exponential of minus 1 by epsilon. This epsilon is a a temperature like quantity, okay. So you know, some epsilon times integral 0 to t L, this L is a Lagrangian, okay, also called the rate functional, which we have been dealing with, which is basically nothing but psi dot plus phi, okay, L z dot comma sigma dt, right. L is the rate functional, right. So the expression for this L actually is in a more general setting is essentially this, okay, phi z dot plus phi star sigma minus sigma z dot, right. Now this sigma z dot with a minus sign is nothing but psi dot, we have already seen that, right. So essentially what it is basically phi z dot plus phi star sigma, phi z dot phi star sigma plus psi dot, out of which phi star sigma is a function of the generalized forces, the thermodynamic conjugates to the rates z dot, and they have to be kept fixed whilst doing the variational problem. We can only vary z dot, right. So you know, virtual variation must be applied to z dot, okay. So you basically see what is actually happening is that essentially the variations in L is organized by this phi z dot and this psi dot, okay. So L is psi dot plus phi z dot plus phi star of sigma. This is anyway, let us hold it fixed for the reasons that I have already described. So basically the variation of L is governed by these two quantities. Now see what is actually happening here in the probability. If L is more, right, then this whole quantity, which is the argument of the exponent, if L is very high, then this essentially leads to almost 0, correct, minus of infinity, let us say. L is very large, okay. So P is very close to 1. On the other hand, if L is smaller, then what happens? L is very large. So what is basically happening? This is minus infinity. Exponential of minus infinity is not 1, it is 0, right. So the probability of that path corresponding to which L is very high is 0, right. So if L is very low, that means if it is the minimum, the lower L is, the higher the probability of observing that particular path for z. That means this shows that L has to be a minimum, right. and this minimizing L essentially means minimizing psi dot plus phi z dot. This is basically the reason why basically we minimize psi dot plus phi z dot. The reason why this particular relationship is true and all that we will not discuss, because that will actually take us completely away from our basic type of things that we basically try to do in this course. It is quite out of scope for this course. But one thing you should remember, that irrespective of the nature of dissipation, be it a system which is undergoing plastic deformation, be it a system which is undergoing viscoelasticity, be it a system which is undergoing damage, irrespective of the nature of dissipation, at the continuum level all these dissipative systems will have such a rate functional L. This is quite universal, it is always true, okay? And therefore the most probable evolution must minimize L, and it will also minimize integral of over 0 to T L, okay? So the integral of L, right. So essentially that is the reason why we basically minimize this, right. So in our constructions typically L is greater than 0, right, and so the minimum because of the very simple reason that basically we construct psi and phi as convex functions, so with a 0 to be the minimum, right. So in that case L equal to 0 is the minimum, so corresponding to, so L equal to 0 is my basically I need to find that particular sigma as a function of z dot for which L will be equal to 0, that corresponds to the stationarity condition, which is sigma is equal to del phi z dot, okay. So this determines the constitutive law corresponds to the corresponding to the 0 cost trajectory, okay. So this actually we have already stated, okay. So basically what we are coming to is the expression for L given by this when holding phi star as a function of sigma fixed, okay. So this is the reason why we basically have this minimization valid, right. So basically what is even more important here is that this connects you up. If you understand that you are actually doing the solution based on this convex minimization approach, with a little bit of modification, if you are interested you can connect it up with with other physical theories, not just with elasticity but with other physical theories, and we can extract a lot more thermodynamic relationship especially valid in the non-equilibrium regime when the flow actually occurs, the entropic aspects which are related to the associated probability flow, etc. So all these details we are not considering here, because we are considering the entire process to be deterministic. Basically we are only considering one possible value of L, which is L equal to 0, right. So we are not making it fluctuating because of the randomness around 0, right. So this is basically a deterministic point of view, right. This makes sense because we are looking at the most probable trajectory. But if you want to look also at the fluctuations, because if you repeat the experiments you will see fluctuations, right. This is a fact, and if you really want to find some information about those fluctuations, then a deterministic theory may not work. So you will have to actually work with the rate functional as an argument of the probability itself, right. So actually characterize the probability properly. So with this we have given a rationale to the reason why we are using the rate functional the way we are. In the next lecture we will be talking about the thermoviscoplasticity of and the time discretization of thermoviscoplasticity of the Perzina type and the incremental potential aspects, right. So we will discuss this for our implementation in the finite element codes of these models, right, in the next lecture. Till then I hope you are enjoying the talks and I hope you are learning in the process properly, okay. So I will see you back in the next lecture. Thank you very much for your attention.